today we started the registration. Next semester, I'm going to offer this class and operating system because it's core courses. And also in addition to them, I'm offering the big data course. Those who are interested in the data, especially the big data platform, you can consider. Also, there's the concentration on MSCS, which is called Big Data and Data Analytics, the concentration. So that requires taking 4 courses. This course, 551, and data mining 552 is currently being offered this semester. Maybe the fall 2018 or the spring 2019. And 2 courses, the 6551, the big data course, will be offered the next semester, and the NoSQL database will be the fall semester or the summer, depending on the department schedule. It will be offered. So if you are interested in the concentration, you can consider the big data. If you already did these 4 courses, including this course, you can just submit the change of your major. It will be reflected to your transcript only, not changing the major. It's the concentration is on your transcript only. Okay, so any question? Okay, so we are going to continue the B3 and the B+3 index. Last time we talked about so before we start the indexing structure, so we have the data file. Data file has the number of records inside, but it's organized by a number of block. So block will be used for the basic I/O unit. Depending on how to organize such each record, so we can have the ordered file, non-ordered file. If you order by certain attribute, it's ordered file. The worst is a non-ordered file. Sometimes we can use the hash using the hash function. So that is much faster, but you need the additional operation. So nowadays, instead of using only the data file, so we can speed up to access such a data using index. So index is the kind of a new data structure. It's also used. That's organized by the number of blocks. Okay, like the data block, we have an index block. So we have the single level index, and sometimes the multi-level index. Eventually this is a tree, but in case of the tree structure, tree index, sometimes it can be skewed. In case of extremely skewed one, this will be the same as the linked list. We cannot get the benefit of the tree structure. The problem of the search tree is because it's a top-down approach. Top-down, it will be going up to the bottom, so sometimes it may be possible to have such a skewed tree. One more thing, whenever we are using such an index, so we need to count number of blocks, how many blocks we are going to use, because the main purpose of using index is to speed up to search the data. At that time, we can calculate the cost of the searching by counting number of blocks. Also, index, for example, 1, 2, then always plus data block. This is the same thing. In case the ID is a 5, it's a pointer this one, 1, 2, 3, 4. So always a plus 1 to count the cost, calculate the cost of the searching the data. So to address the problem of using search tree, which means it's unbalanced one, we are going to make a balanced tree. That's the idea of the B3 index. Unlike the search tree, the B3 index is growing bottom to up. So search tree, you can build the search tree top to always from the root and going up to the bottom. So that causes a problem. So we are going to use the B3. When we are talking about the B3, it's called the balanced tree. So balanced tree has the node. So it is very important to design the node structure in case the P is equal to 3. So index node has this is the illustration purpose. Okay? if you are implementing this indexing structure, it will be data structure. For example, if we are using Java, this node will be class, one class. Inside, how many data you use is the design. So it's a data structure, it's an illustration purpose. So, for example, in case of P order 3, order 3 means how many children pointer? In case the P order 3, this is order, P is 3, how many child pointer, children pointer? It has the 3 children pointer. Definitely this will be your final exam. Okay? So then how many index key entry? 2. Because we have the 3. So for example, this is a 5, this is a 10. That means this is like the 5 pointer, this one. And 10 pointer, this one. What is this solid pointer? This. What is this?
Pointer to data entry.
It's a point to the data file pointer. Like if you think about the index of your textbook, it's a page number where your keyword is found. Okay, so this is the data pointer. And what is the white one? This is the pointer of the child the node. So which means less than 5, all the index key entry less than 5, like the 1, 4 will be in this children node. And bigger than 5, less than 10 goes to here, like the 6 or 8. And bigger than 10 goes to here. Okay, this is the idea of the node tree structure. It's similar as the tree. However, to make it balanced, we are going to build the tree structure bottom to up, which means first we are going to find the leaf, the node, is where it should be inserted. Then, if there is a available key entry, that means so you can just insert, okay, the index key entry. However, if your node is full, what happened? There's no more space, so you need to split into the 2. Then, like the 9 will be inserted. 6, 8, 9 among the available value. First, identify which one is the middle one. So less than middle goes to left hand side node. Bigger than middle, right hand side. And middle value will be promoted. Promotion means going to the parent node. You can insert. What if the parent is also full? You can do the same thing. Split and promotion until you find the location of all of this. So, for example, so I'm going to explain again the B3 index for this one. When I show this sequence of number, what does that mean? This is the key entry value, okay? Index key value. So real data will be like this. Insert into the student values 8 and name is Lee and address is blah blah like this. And next one will be 5, but to simplify, okay? So I'm going to use only index key entry. So in real life system, it will be like the insert into all the record, and then this data will be inserted where? Data block. Here, the A, Lee, like this. 5 will be like the James. This is the entire record that will be inserted to the data block. But we are going to build the index, index structure. Okay. Before you start, for the index, you need to design the index node structure. It's a B tree, and also order is 3, as we have seen over there. How many children pointer? 3 of them. How many index key entry? P minus 1, 2. Like this. This is a node structure. In other words, if you implement the B3 index, you can define your class, node class, then instantiate. Okay, you can use the new command. You can instantiate and to your memory it will be. If this is a memory-based index, what if you are using the file, index file? You can create a file instead of instantiation. Okay, create the file for this index tree, and the index file has one node. It's a one block. Okay, this is the same level. Hardware level, low level is the same as the block. Okay, where is the block? In your hard disk drive or solid state. It has a number 0, 1, 2, 3. One block, available block will be assigned to this one. Okay, then go back to here. So this is our the B3 node structure. One more thing. What if order P is equal to 4? In this case, it will be how many children pointer? 4. How many? So 3 index key entry. So this will be the data pointer. This will be children pointer. So we are going to use P equal to 3. Then, so 8 is inserted. Nothing, so we can create the one node. Same node structure like this one. Okay, no children node. It's a null pointer. All of them are null pointer. And no data pointer. Then 8 is inserted. Then this one will be solid. Solid means it's the pointer is assigned. Is probably pointer this block. Okay? But the full simplification, so I'm not going to point each and everything, instead just to illustrate using the solid. So let me erase this one. But it should be in your real application. So that is after 8 is inserted. What about the li and everything? That those attributes will be inserted in the data block. Okay, but we learned before. I'm not going to explain add this one. So only focus on. I'm going to focus on the index structure. Then next, 8 is inserted. So we have space, so we can easily sort the data. Quick question. It's just a simple question. What about the sorting the data within a node? Is it difficult or it's just simple? What if we have the 100, the index key entry, like the P is 101? Still, it's a very simple. Why? This block will be where? It's a memory. You can, whenever you read and write the file, it should be on the memory, then write to this drive. So this sort will be done in the memory. It's a one block, one I/O. So the sorting the data within a block is just a piece of cake. So you can ignore such an overhead.
So it will be on the heap or on the stack, the memory.
This one?
Yeah.
So this one depends on how you define your program. Okay? So when you write the file, okay, so you need to open the file. If there exists the file, so you can read the block to the memory, update, and flush to the hard disk drive. It's the same thing. Okay? So because some of the students curious, the Professor Lee just said the within a block is just automatically sort. Yes, you need to sort, but that cost is not expensive because it will be done in the memory within an I/O. Then this is done up to the 5. The next 1 is inserted. Inserting 1 means the entire record that include the 1 will be inserted. Then 1 should be inserted. It's full of the node. So in case of full, what happened? So 1, 5, 8 should be managed. Okay, which one is the middle value?
5.
5 will be the middle value. Then split into 2. Just copy same node structure. Then 1, 8. The left hand side of the middle value, left hand side node. Right hand side of the middle value, right hand side. Then next, the middle value 5 will be promoted. Promotion means, is there any parent node? No. So we can create the same node structure. Then 5 will be inserted. One more thing is, we need to check the pointer. This time it will be solid. And bigger than 5, go to here. This pointer means children pointer is a block. Always we can use the block ID for the pointer. So that's it. Here, another quick question. Let's say the P is equal to 4. So we have 1, 2, 3 already. And 4 is inserted. So it's a 4, so we need to decide the middle value. Which one will be the middle value? Either 2 or 3. Either way is fine. So if you see the textbook, it will be like the P over 2, like the floor or the ceiling, something like that. It doesn't matter as long as you have consistency. So in this classroom, we decide to use cardinal half and the left hand side as the middle value. Some of the implementation used this one as the middle value. But either way is fine, but for the consistency, we will use this. So 2. In case the even number of the data. Okay, so that is up to the 1. What about 7? We need to find the proper node. So that should be inserted. 7 is bigger than 5, then go to here. So it will be inserted. So 7 is here, 8. Even though we have the space, we do not insert here. Okay? Don't be confused. Always we need to find, because it's a bottom-up approach. So always bottom-up approach, why? To keep the balance. If we have the leaf node, always it's the same level. It's a balance. Then 7 is done. 3, less than 5. Even though we have the space here, we do not use until leaf node. So 3 will be inserted here. The next 12. 12 is inserted here, but even though we have space, we do not insert to the root node or internal node. We need to find until the proper node. So 12 is bigger than 5, so bigger than 5 goes to here, but it's a full. So 7, 8, 12. So which one is the middle value? 8 is the middle value, so we can split into 2. And 7, 8, 12. Left hand side, 7, right hand side, 12. 8 will be promoted, then insert the 8 here. Is there any space? Yes, there's a space, so 8 will be inserted. Then check the children pointer. Then that's it. So 7, 12 is inserted. 9 is inserted. 9 bigger than 8, and 9 will be here. And 6 is inserted. Bigger than 5, less than 8 goes to this one, and 6, there is a space. Okay. So this is the output of the B3 index after inserting in this sequence. Yes.
What about if the number less than 5? Which one I have to choose?
So, for example, 0 is inserted. So, bring your any scratch paper. Bring your scratch paper right now, okay? And draw the next one after inserting 0. So if we insert the 0 over here, how this index will be changed? Anyone who is done? Okay, why don't you solve the problem here? You can draw the new one over here. Why don't you see the answer? Okay? So what do you think? Is it correct? No? No? Let's check that together. So when 0 is inserted, you need to find the location. So 0 is less than 5 and the probably here. So 0, 1, 3. So 0, 1, 3, which one is the middle value?
1.
1. So 1 is promoted. So we will check that later. So 0, 1, 3. So 0 is split. So if we split, left hand side and right hand side. Okay. Then the middle value will be promoted. This is good. Then the other will not be changed. The original. Then when we insert the promote, the middle value 1, 1, 5, 8. So we have 1, 5, 8 decide the middle value. So 5 will be promoted and the 1 and 8. This is good. So then we need to check the older children pointer. At the children pointer, 1 less than 1 goes to here. Less than 5 bigger than 1 goes to here. Bigger than 5 less than 8 goes to here, and bigger than 8 goes to here. So this is the probably correct answer. Then we can keep doing if we have the more data inserted. Okay. One more question before we take a look at the B plus 3. So how many I/O do we need to access the data? Like the, for example, select SRS from this is a student table, and where ID is equal to 6. How many I/O do we need to access this data, the query? 1, 2, 3, then using this one, and 6. So how many? 4. What about the 3? 1, 2, 3, 4. What about 5? 1, 2. And what about 1? 1, 2, 3. So how many I/Os do we need? Maximum 4. Or sometimes less than 4. Because B3 index and has the upper bound. So it's not unbalanced. It's a balance, but because of internal load, it's a less than something maximum. Okay. So it's not perfectly balanced. There is a maximum, but sometimes it's very quick, sometimes very long. So later, when query optimizer decide to go to the, for example, do you remember I gave you the example of visiting the traveling to the Manhattan? So how long it takes? MTA 1.5 hours, and sometimes 2 hours. So if you have the maximum time, sometimes 30 minutes, sometimes 1 hour, sometimes. If that is fast, you need to wait, right? So even though you have the maximum, so it's not perfectly balanced. So from the query optimizer point of view, when you schedule, it's better than the search tree, but still it's not perfect to schedule your time, right? So this is one of the problem of the B3. When you have the level 3, it's okay. But when you have the 100 level, 0, 1, and 100 are totally different. If you especially have a lot of transaction, so huge difference. So query optimizer confused with whether this is really good choice or not. Okay? So we try to address such a problem by considering the B plus 3. B3 and B plus 3 are very similar, but B plus 3 is the perfectly balanced. So what will be the idea? Problem is, this is an internal node, root node and internal node. These are the leaf node. Leaf node and also internal node, 5 and 8. This node has the data pointer. Because of that, it takes a shorter time. This one, longer time. So what if we move down all the data pointer to the leaf node? Only leaf node has the data pointer. Then it will take the exactly same time, which means same I/O, same level. Okay, so how can we do that? First, we need to consider two different node structures. One is the internal node. Another one is the leaf node. At this time, if we consider P is equal to 3, that means P leaf. The same idea as that one is a 2, which means how many data pointer we can have? P minus 1. P is the children node pointer. So this time P leaf, because later we will see why it's called the P leaf. P leaf is the 2. So internal node means leaf node first. Leaf node, is there any children pointer? There's no children pointer, right? Leaf node is the last terminal node. There's no more children. So we can define the only index key entry. How many? P minus 1. In case of order P is 3, P minus 1. How many index key entry? 2 of them. And one more. I will explain this one later. Okay? This is the simplified, the leaf version. Because you can see the leaf node, actually it's a null pointer. We don't have to keep. The reason is that internal node is different from the leaf node. Internal node will be children node similar as this one. It has only, what's the difference between this one and this one? This one does not have data pointer, which means since we are moving down all the value, all the data pointer to the leaf node, this one does not have the data pointer. This will be like this one. Then, what is the meaning of this value? It will be used for branch condition. Whether less or greater, no data pointer, just branch purpose, it will be used. So we will see. So there are two types of node here. That's the different from the B-tree index. So leaf node has the only data pointer, but it doesn't have a children pointer. Internal node has the key, but it's not data pointer. It's